Okay, so this extra half an hour, we needed that to conclude the problem. So let me share the screen again. So at this point, I arrived at this at these results, right? So I know something about RT, but that depends on these unknown functions, unknown evaluations of the value of being at state 0 or being at the danger state, right? So what I want to do is to write the continuation value more simply. So for this, I'm going to do that. So the continuation value is what? So I have the formula here. So it is V0 so it will be, let me write it again. So it will be theta r square, right? Theta r square times V eta plus 1 minus theta r square times V0. All right. So if you rewrite this, you have V0 minus V0 minus V eta theta r square. Okay, of course, this is RT. Okay, now remember that RT square, we found it as alpha divided by 2 theta beta. Is that correct? V0 minus V eta. Okay. So theta RT square V0 minus V eta is equal to what? Alpha divided by 2 beta, right? Sorry, V0 minus, yeah. Okay, so then your continuation value, so but basically I'm writing this, okay? Expected value of V dt plus 1 is going to be equal to beta V0 minus alpha 2 beta, okay? And RT, let me also write ln RT. ln RT will be equal to what? So I know what RT is. So I have something like this. So ln, you must confirm these things later on, okay? You work on this because I'm writing the solutions quickly. So you have one term that tells you this, and then you have this other term which is equal to that. Okay, you must confirm this. Now denote this term by, let's say, omega. All right, for simplicity. Now what I want to do is to write these things, V0 and V eta. Okay, so V0 is what? It is alpha ln t. So sorry, alpha ln RT, right? So I have alpha omega minus this, okay, plus the continuation value. Why? Because d is equal to 0, right? So the continuation value is V0 minus alpha divided by 2 beta, okay? And for V eta, this part is the same, right? This is alpha ln RT, but now I also have ln 1 minus eta, right? ln 1 minus eta and then the same continuation value. Because I chose R optimally, right? Now this thing is a negative number, right? So let's denote it by that, where gamma is positive, okay? Because eta is very close to 1, but less than 1. So this number is between 0 and 1. So this whole thing is negative. So minus gamma with gamma positive is that number, okay? This is just for notation, by the way. Now, I also want to simplify the notation by this. So let's suppose that V eta, not eta bar, obviously, V eta divided by V0 is, let's say, X, okay? X is some unknown here. And V0 is, let's say, V, okay? So X and V, unknowns. We want to solve them, right? So how to do it? Realize that now I can write my system in this way. V equals, so the first equation, V equals what? Alpha omega minus alpha 2, oh wait, we have ln here, okay. There's ln here and ln here, okay. Alpha, ln, careful. So this is what? V minus xv, right? Plus beta V minus alpha 2 beta, okay? And here I have xv equals alpha omega alpha 2 ln, the same thing, right? V minus xv minus gamma plus beta V minus alpha 2 beta. Okay. Now, what do I have? I have two equations and two unknowns. Right? You see that? I have two equations and two unknowns. So in principle, we can solve it. All right? How to do that? Well, you're going to realize one thing. You're going to realize V equals xv plus gamma, right? Right? I'm double checking my solution, by the way, but this must be true. Then there's a relationship between, so you have V equals, so 1 minus x that, then V is equal to gamma divided by 1 minus x, okay? So then if you replace 1 minus x that you will see here, okay, then you will have one equation with one unknown. And then you're going to solve V. And that V is equal to, let's do it here. Okay, let's do it where? So I have V equals what? Alpha omega alpha 2 ln gamma, right? Because this is now 1 minus xv plus beta v minus alpha 2 beta. Okay, so then I have v equals alpha omega alpha 2 ln gamma beta v minus alpha divided by 2. So we have v being equal to, so 1 minus beta v alpha omega alpha 2 ln gamma minus alpha 2. So v, in other words, v0 is equal to alpha omega alpha 2 ln gamma alpha 2 divided by 1 minus beta. Then V1, then you're going to find, of course, x using V1 minus x is equal to gamma, right? Yes. Then you're going to find 1 minus x is equal to gamma V, x is equal to 1 minus gamma divided by V. Then V1, V eta is equal to what? V eta is equal to x times V0. So you have that. Okay. Then you got it. That's your solution, because now how is that your solution? Because now you have RT, right? So you eliminate V0 and V1, so you find RT only as a function of parameters, right? Because you find V0 as a function of parameters. You have 1 eta as a function of parameters. So once you replace these things, you find your control. And then, of course, this is, don't forget, this is stochastic, right? So it is equal to eta with probability theta RT2, but you know exactly what this is equal to as well, right? Because once you have RT, then you also have mu RT as a function of parameters only. Okay? So then it is equal to 0. So this is with probability, and this is equal to, so let me be more formal. So this is equal to with probability mu RT and equal to 0 with probability 1 minus mu RT. So if you look at this from the viewpoint of a time series, for instance, you're going to see something like that. So if this is t, if this is dt plus 1, this is eta, and this is 0. Okay? So in some let's say in some periods, it will be equal to eta. In some periods, it will be equal to 0. Okay? But this choice will be, of course, optimal. All right? Something like this. But your your R, remember that RT is between 0 and gamma. Under certain parameter restrictions, it will always be equal to R star. Okay, so there is a variable risk. So we understand the dangers of the technology, but we also understand the benefits of it, right? So we choose research technology spending optimally by taking into account the continuation value and how a disaster would harm us, right? So this doesn't mean from an ethical or normative point of view that should be the welfare maximizing policy from an ethical point of view, etc. But this is what we have. If we are assuming that this decision maker is rational, perfect information, etc., then he or she can calculate the risk involved. Then, given that risk, he or she can calculate the continuation value under the spanning R star, etc. Right? R star could be the optimal, and in this model it will be fixed. So then we have the solution. Okay, and how do I know that there's only one path? Because I know that my reward function is strictly concave, right? Because there's this alpha ln RT term. Oops. So since this is in the reward, this is strictly concave, and this is never optimal. You also understand that, right? This is never optimal. Okay. So now we have we arrived at a point where we can conclude. So that was a long semester. We covered basically two things. So two general things. One is nonlinear programming. This is basically static optimization. And the other thing is dynamic optimization. Okay, so this class is actually a course in optimization theory, as you realize. In between, of course, we study dynamical systems, both in continuous time and in discrete time, because in dynamic optimization models, either in continuous or discrete time, we have a dynamical system that characterizes the optimal path. Okay, so we want to understand such dynamical systems, but we also studied how we can find those dynamical systems that characterize optimal paths. Okay, so to do that, in continuous time, we used Hamiltonian approach, and in discrete time, we used mainly the Bellman equation approach. Okay, because those recursive methods in dynamic programming simplify the analysis a little bit. One omission was stochastic models in continuous time. We can also cover that, but we have no time for this. I think discrete time is much more interesting, and its practical significance is a little bit more obvious, because time is, once you want to take such models to the data, what you observe is discrete, from month to month, quarter to quarter, year to year. So discrete time is much more practical in that sense. But if you want to see how you do this in stochastic continuous time models, what we use there is called Hamilton-Jacobi-Bellman equation. So it's a mix between Hamiltonian and the Bellman. It looks very much like the Bellman equation, but techniques are a bit more involved, because stochastic systems in continuous time are much more difficult to study. It requires certain advanced mathematical tools, which is beyond the that are beyond the scope of this class. Okay, so I'm going to stop here. We have time for your questions and comments, and then as we discussed before, your final exam will be executed as a distance exam. We're gonna benefit from the online education systems. So the date was, I took notes. I think I'm gonna put this on January 22nd, right? Friday. I'm gonna upload it, and then you're gonna upload it back, your answers, on 26th of January. All right. So we have time. Again, if you have questions, comments, I can try to answer them, or to respond to them. Nothing?
Sorry, I have no question so far, but thank you very much for your patience and for your great teaching.
Thank you. You're welcome. I mean, I'm just trying to do my job.
Thank you.
Thank you.
In the best possible way. All right then. So I'm gonna upload these as well to YouTube, so you can always watch back. Just play with these models. All right. I mean, for any topic, you learned a lot, right? I mean, you learned continuous time models, you learned discrete time models, linearization, normalization, finding steady state, understanding the phase diagrams. So there's a lot of material, and the last topics were, of course, a bit demanding. So I want you to understand the logic of value function iteration, policy function iteration, guess and verify, and the first order conditions and the significance of writing down the continuation value, taking into consideration, the decision maker takes into account what happens in the next period. So you also, as the researcher, you also need to take into account what will happen under certain control choices. I mean, certain controls, what will happen given a particular state. So that all requires a bit of effort, of course, because in the first time you study such models, it's a bit difficult, but not necessarily very complicated. So if you get the logic of Bellman equation, or if you get the logic of the Hamiltonian and the call-state variable, then it is all very meaningful. I mean, go back to the monopoly problem that we studied today. You're going to understand why continuation value matters, right? Because my pricing today, yes, I want to maximize my current profit, but in the meantime, I'm caring about my future profit, and my future profit depends on my demand, and my demand in the next period, my future demand depends on my pricing position. If I'm very violent by setting very high prices, that will hurt me. Okay, so that type of dynamic trade-offs, that's the important part in dynamic optimization models, obviously. So you want to, so in some questions I have, for instance, in some exam questions, I just give the problem and I just ask, not the solution or etc. I just ask, what is the dynamic trade-off? Explain the dynamic trade-off here. All right. So that's an important thing to do, understanding the dynamic trade-offs. And in sometimes, in some problems, some control variables will be static, as the labor in our firm problem today, right? Because the choice of labor does not really change my capital stock in the next period. I mean, it will be determined period by period in a static way. Okay, so those nuances are important. Okay.
Okay.
All right. So I wish all of you a productive final exam week. Good luck in all your exams.
We hope so.
And you will find all my questions and other stuff. I already sent the links, past exams and past homeworks, so you can also work on them to study for the final exam. Okay. I thank you and have a nice day. Bye-bye.
Okay,
Thank you.
Thank you.
Thank you.
Thank you.